All right, so what we'll do today is we'll talk about binary number comparison. In other words, how do we know whether a particular value represented by a binary number is greater than or not than the value of another binary number? Okay, so that's what we want to find out. The first thing we notice is with all the comparison operators that you have learned in cisp360 and also a little bit before that in cisp300 or 301, you only need one. Okay, they give you a whole bunch: less than, greater than, less than or equal to, greater than or equal to, and then not equal to. But you really only need one of them. Okay, the rest, the other five, are actually kind of redundant. So this part here shows you how we can get away with only one single comparison operator with the assistance of logical operators, and or not. Okay, less than, it's just less than, no big deal, that one easy peasy. The other one, next one, is easy too, because if you want to find out whether x is greater than y, you can always just reformulate to ask whether y is less than x. Okay? If you want to know whether x is less than or equal to y, this one is a little bit tricky, but I think most people get it right away. You can ask the question of, is it not that y is less than x? Because if y is not less than x, then y is greater than or equal to x, or x is less than or equal to y. Is that making any sense? Okay, all right. So the next one is just transposing the x and the y. If you want to know whether x is greater than or equal to y, then you can always ask the alternative question, which is equivalent, of whether it is not the case that x is less than y. Okay, kind of the same thing as the one before, just flipping the positions. The next one is, what if you want to know whether x is just different from y? Well, as long as x and y are numbers or integers, x being different from y means x is less than y or y is less than x, right? So once again, we boil down the comparison operator to just less than, but this time we need a logical operator to help us out. And then the last one is you want to know whether x equals y. Well, x equals y is the negation of x does not equal to y. So we just negate the one before. So we just put a negation to the expression that is equivalent to whether x is different from y. So what is the bottom line of this? You're looking at all these are pine needles. You take a step back, the pine tree is basically saying you don't need all the comparison operators. Less than is all you need. Now, if you prefer greater than, that's fine too. Okay, but in this class, we focus on just less than. Is that okay? But there's a little bit more that is not written here. With all the logical operators, I can now say, oh, but wait, we don't need all these operators, logical operators, because all we need is NAND. This is going all the way back to week 1, the first class. Okay, was when we introduced the NAND 2 gate. Remember that? That was implemented by 2 P channel MOSFETs and then 2 N channel MOSFETs that implements a single NAND 2 gate. But all the other logic gates, not, and, or, they can all be implemented using the NAND 2 gate. So that means to do all the comparisons in C and C++, all you really need is less than and a NAND gate, or multiple NAND gates. But the construct-wise, that's the only kind of logical operator that you need. Okay, yeah? Less than AND gate are the only 2 constructs you need to reconstruct everything else that you have learned in CISP300 and 360. Doesn't mean that it is easy to read, because if you think about the OR by itself, is already a pretty nasty, if you want to express OR using NAND, it looks kind of long and nasty, okay? And then on top of that, you need a negation, so that makes it kind of ugly, okay? It looks ugly, but it can be done. All right? So do we have any questions about that kind of interesting observation? No. Okay. Is there no question, or you just disagree that it was interesting? Okay. So the first part here talks about unsigned comparison. So unsigned comparison, so I only need to know two facts, okay, before I can do unsigned comparison. I need to know that 0 is less than 1 is true. I also need to know that 1 is less than 0 is false. Okay, those are the only two things I need to know ahead of time. I mean, would you agree that 0 is less than 1 is true? 1 is less than 0 is false? Okay, so we don't have any disagreement here. So what we do next is we have the notations just like before. So we have this notation. We're comparing x to y. Okay, we are trying to figure out whether x is less than y or not. Okay, remember, I don't really care about greater than or equal to, less than or equal to, or not equal to. I just need to know whether x is less than y because I can derive all of the other comparison operators from just less than. So my only concern is less than. And then we use the same notation. X with a subscript of I is representing bit I of a binary number x. Okay, so same notation as before. And the same thing for y. And then we also know this is really just a kind of recap of what we know from before. So we also know that xi as a single bit, a single digit of a binary number is representing the quantity, but since it's a binary number, when we talk about the quantity, it really is just absence or presence. It's either there or not. Okay, it cannot be more than 1. Of 2 to the power of I as the magnitude, so we are just trying to express, okay, is there a quantity of 2 to the power of I? That's the job of xi, digit I of a binary number x. Okay. So we also know, okay, intuitively you might say, well, we also know that 2 to the power of n, pick any n, okay, pick n equals 1, pick n equals 2, and so on. So n has to be a positive integer, so 1 and above. 2 to the power of n is greater than the summation of I equals to 0 up to n minus 1, and then the term that we are summing is 2 to the power of I. Does that make sense to you? Does everybody know what this comparison is trying to express? Yes? No? Okay, no. Okay, that's fine. So we'll go ahead and explain that. So what that expression is saying is 2 to the power of n. Okay, let me pick a medium thickness. So what it's saying is 2 to the power of n. Okay, excuse me, we cannot drink in the classroom. So maybe later. So 2 to the power of n is greater than 2 to the power of n plus 1, oops, n minus 1. So let me undo that. N minus 1 plus 2 to the power of n minus 2 plus 2 to the power of n minus 3, and so on all the way up to, or down to, 2 to the power of 0. Okay, sorry? But how do we know this is true? Just because I claim that it is true doesn't mean it is true. Now, you guys missed this part. Some of you did. Okay, some of you, heard me saying that. But according to the analysis of my personality, my conscientiousness is only at 13%. So you need to question everything that I say. Okay? So when I claim something like this, then you ask, why? Yep. Say that. Yes, so the idea is to prove this by induction, okay, which is a proof technique that I would teach in CISP 440, and I know this is CISP 310. I did not get confused. But nonetheless, I need a way, I need to show you that this is true. So proof by induction. Okay, first of all, do we understand what we are trying to prove? Okay, this is the theorem, and it is an expression, or it's a condition, it's a statement that I claim is true. But how do we know this is true for all the n's that are at least 1? Okay, that's the question. It seems to work out when n is 5, right? When n is 5, 2 to the power of 5 is 32, right? 32 is greater than 16 plus 8 plus 4 plus 2 plus 1, which is 31. Okay, it just beat it by 1, but it is greater than. But how can I generalize and say that, oh, you can pick any positive integer of n and it will still work? That seems to be a jump right there. So how do we know? So we can prove it. And to prove this, we use a proof technique called proof by induction. So with proof by induction, I'm not going to focus too much on proof by induction in this class, but I will give you the exposure, because sooner or later you will be exposed to proof by induction. You might as well get repeated exposure to the same concept, because that way the next time you encounter the concept, you go like, yeah, I have some vague recollection of that concept. It might sink in better the next time you see it. All right, so proof by induction has 2 steps. The first step is to identify what we call a base case. So the base case typically is if the statement has a variable, like n in this case, you pick a specific value of n, and we typically want to pick a value that is at one end of the entire collection of values that n can assume. Okay? In this case, because n has to be 1 or more, n equals to 1 is, well, one of the extremes, so we'll just pick n equals to 1. So the base case is basically saying when n is 1, okay, can we prove that the theorem applies for that specific case? What do you think? When n equals 1, then the comparison is easy because it's only comparing 2 to the power of 1 to 2 to the power of 0. 2 to the power of 1 has a value of 2. 2 to the power of 0 has a value of 1. 2 is greater than 1 is true. Okay, so we got that. Is that okay? All right, cool. So the base case of proof by induction typically is just like that. You plug in an actual value into the variable in the theorem, and you just say that for that specific case, the theorem holds true. Okay? Then we have the induction step. The induction step, which is this part here, is interesting because the induction step starts with an assumption. The assumption is the theorem is true for some specific value of n, and that's just assumed. So in this case, I'm just using k as a symbol to say that, okay, we assume that the theorem is true when n equals to k, and therefore 2 to the power of k is greater than the sigma of I going from 0 to k minus 1, 2 to the power of I. It's an assumption. I don't even care about the actual value of k. I'm just saying that there is a value of k that is at least 1 where I can prove that the theorem is true when n equals k. Okay, so the magical part is from that, can I show that 2 to the power of k plus 1 is greater than the sigma of I going from 0 to k, and then each individual term is 2 to the power of I. Okay, so in other words, assuming the theorem is true when n equals to k, can I use that assumption to prove that when n equals to k plus 1, the theorem holds true as well? Okay, that's the key of proof by induction. It's just that one step, that one small step. Can we take that one small step? So the proof here is pretty normal, pretty easy. 2 to the power of k plus 1 is greater than sigma. I goes from 0 to k, 2 to the power of k. That's what we want to prove, okay? And then I just have to express 2 to the power of k plus 1 as 2 to the power of k plus 2 to the power of k. Is that okay? Okay, because it's basically 2 times 2 to the power of k, so I just write it out as a summation. Is that okay? And then on the third step, let me scroll this up a little bit. So on the third step, I just subtract 2 to the power of k from both sides of the inequality. So if I take away 2 to the power of k from the left-hand side, I got one of those left. But if I remove a 2 to the power of k from the right-hand side, I only have to change the sigma. Instead of ending at I equals to k, now it ends at I equals to k minus 1. Is that okay? So there are really kind of tricky things you can do with the sigma notation, because you can just take out the one end or the other end. Okay, so a lot of tricks involving sigma or proofs with sigma has to do with the ends. How do you shift the end or reduce one item from the end and stuff like that? But wait, we have seen this before. What was it? It was the assumption, exactly. It was the induction step assumption. So we linked the step all the way back to the assumption step, to the assumption. So now this basically concludes the proof that in general, okay, as long as k is greater than or equal to 1, 2 to the power of k, 2 to the power of n is greater than the summation of 0 going to n minus 1, 2 to the power of I. Okay? Is that okay? All right. If you don't fully understand proof by induction at this point, don't worry. Okay. In this class, we are not going to have any proofs. You are not going to have to do any proofs involving proof by induction. It's going to be a topic in CISP 440. Okay. But it is nonetheless a very interesting way of proving theorems, and it's really handy for a lot of different things. So what I do next is I then look at x and y. So x is a binary number, y is a binary number, and they have m explicit bits. In other words, if you're talking about 16-bit numbers, m equals to 16. And I say explicit bits because they're always implicit bits to the left-hand side of numbers. Okay, I'll give you an example. 16, okay? So 16 in base 10 is 1, 6, right? As a number. Where are the implicit digits? To the left. And what do you think are those digits? They're all zeros, okay? You can always assume that it has an infinite number of leading zeros from the left-hand side when you only say, oh, 16, but it can also be written as 016 or 0016 or 00016 and so on. So that's why I use the word of explicit bits, because those are the ones that we're actually storing in the computer, even though it has an infinite number of digits to the left of those explicit digits. Okay, so given that m has explicit bits, we assume x equals I equals xi equals to yi equals to 0 for all the I that are greater than or equal to m. What does that mean? That means x subscript m equals to y subscript m equals to 0. So in the case when m equals to 16, that we're dealing with 16-bit numbers, we're basically saying bit 16 of x and y are the same because they're both zeros. Okay, bit 17 are both zeros. Bit 18 are all zeros. Does that make sense? All the implicit bits to the left, or the more significant digits, are just implied zeros. But since both x and y have exactly the same implicit zeros, so they're all the same. Are we okay with that? Okay. The next paragraph is, you can ignore this one because we actually do not need to use a subpart of a binary number, so we don't need to understand this notation, at least not in this slide. So now we get into the steps here. So what we do is we make an assumption that xi equals to yi for all I greater than or equal to p. So p is really a variable that starts from m, and we want to work our way back to 0. Is that okay? So p is a loop variable from a high number, which is m, working ourselves back. Okay. The next statement says, okay, so with a new value of p, okay, because it keeps getting smaller and smaller, if x subscript p equals to 0 and y subscript p equals to 1, then we can make a conclusion that x is less than y. In other words, the first bit from the left that is different, we look at which one is a 1 and which one is a 0. If x is the binary number that has a 0, while y is the binary number that has a 1, and that digit, xp and yp, are the first digit from the left that are different, then we can conclude that x as a binary number is less than y as a binary number. How can we make that conclusion? Just because one bit is different. It had to do with a theorem that we have proven earlier. Because using this, we can now say that y has to be greater, because even if all the remaining bits of x are 1s and all the remaining bits of y are 0, it will still be true that y is greater than x. It had to do with the theorem that we proved earlier. Is that okay or not? Yes, no, no. Okay, so maybe a picture can be can be helpful here. So basically what we are looking at is, okay, so we'll have two rows, okay? We have x and y. And these are the least significant digits, the second least significant digits, and so on. And then we have a whole bunch of zeros as the leading zeros, okay? And then at some point we get to xm minus 1, which is the actual represented bit of x, and then we have ym minus 1 as the actual represented bit, okay? And then at some point we get to xp and yp. So what we are saying is all of these bits are the same. So from x subscript m minus 1 all the way down to x subscript p plus 1, they are identical to y subscript m minus 1 all the way down to y subscript p plus 1. So these bits are identical, which means and when we are not considering xp, yp, we can't really quite tell which number is larger or which number is smaller. Does that make sense? Because they all have the same bits up to this point. Okay? So now we basically say that we focus on xp, yp, and then we say there are three scenarios that we have to consider. Okay? xp, yp, and then we have to say, okay, what is the conclusion? Conclusion. Okay, so the first one is, what if xp is a 0, yp is a 1? The conclusion is less than is true. X is less than y is true. So now the question is, how do we know that? Is that okay? So everything to the left of xp and everything to the left of yp, all of those are identical between the x and the y. Okay? And now suddenly we say that, oh, xp is a 0 and yp is a 1. How can I make that conclusion that x is less than y? Now, in your mind, it is intuitive. This is how you have been doing comparison with base 10 numbers all these years. But why does it make sense? And is it always true? Well, we haven't really looked into that, have we? That's why we had that theorem earlier. Because if yp is a 1, okay, I can use a different color. I can undo that later. So if I use a different color, I'll use green here. So if yp is a 1 and xp is a 0, okay, this is the scenario that we are considering at this point. Somebody suggested me using a team viewer or team view in place of what I'm using here. So I will try that out, when I have time, because the lag time of this software is really too much. Okay, so now the question is, if I know xp is a 0 and yp is a 1, how can I conclude? I don't have to look any further. I know x is representing a value that is less than the value represented by y. How can I make that conclusion? Okay, what is the worst case that can happen here? Maybe the rest of y, they're all zeros. Okay, maybe the rest of x, they're all 1s. Okay, so now the question is, in that case, how do we make sure that x is still less than y, even though x has all the 1s, to the right of xp, and y has all zeros to the right of yp? Yep.
That particular bit is greater value than all the bits put together.
Yep, but how do we know that? The theorem, exactly. The theorem that we just proved earlier said that 2 to the power of p is greater than 2 to the power of p plus p minus 1 plus 2 to the power of 2 to the power of p minus 2 all the way to 2 to the power of 0. That's just what we have proven earlier. So this is the reason why we can have this conclusion that if xp is a 0, yp is a 1, we can now conclude that x is less than y. We don't have to look any further. Okay? So are we relating the theorem that I have proven earlier to the reason why I can make this conclusion here? Okay? All right, same thing. If I have the opposite, oops, let's undo. Okay. So I'm going to undo the green part too, because the next scenario, I'm going to use a red color. It's okay, it's all getting recorded, so if you replay the video, you will be able to get back to it. And if you think that you might want to get back to this part, you might want to write down the current time, which is 9:32. So it's about 32 minutes into the recording. So this makes it easier for you to just locate that frame that you want to look at again. Okay, so the next one is, what if xp is a 1 and yp is a 0? Then we can already make a conclusion that x is less than y is false. Now, how can I make that conclusion? Yep, it's lagging behind a little bit here. So this time I'm going to use a color of blue and say that this time xp is a 1 and then yp is a 0. Well, it's kind of the same deal as before. So the worst case I can assume is everything to the right of xp are zeros and everything to the right of yp are ones. But based on the theorem that we have proven earlier, even in that worst case scenario, x is still not less than y. Okay? So that's why I can already make a conclusion. Okay? I don't have to look any further. What if they're the same? If xp and yp are the same, then what do we do? Okay, so they can both be 1s, they can both be 0s. So if that is the case, then we move p. In other words, we decrease p by 1 and just say that, well, we don't have a conclusion. Let's go ahead and move this to the right-hand side by 1, and then we compare those bits again. Is that making any sense? Say that one more time. So if xp and yp are the same, which means they're both 1s or they're both 0s, then I cannot make any conclusion because, hey, I cannot determine as a number whether x is less than y because so far they are equal. So what I need to do is not to draw a conclusion about x and y, but to move the p index to the right-hand side. P gets decremented. Okay? So at decrement p, then I will be looking at another digit to the right-hand side of the current xp, and I repeat this entire exercise. Okay, I look at xp and yp and say, okay, are they different? If they are different, I will come to one of these two conclusions. If they are the same, then I have to move it again to the right-hand side. Is that making any sense? Until we get to the last digit. If these two are the same, then we have to say, whoops, sorry, x is less than y is false because those two numbers are the same. Is that okay? All right. So moving along in the notes. So now the question is, all right, so now that we know, how we can look at the bits and find out when to stop and how we can determine which number is smaller, when we perform a subtraction, what can we do? What is the indicator that x is less than y? X being a binary number, y is a binary number. Well, as it turns out, we can use something like this. Now, when I use the v function here, v of x and v of y, we are just emphasizing that we are talking about the value represented by x and the value represented by y. Okay, so this is saying the value represented by x is less than the value represented by y if and only if the borrowed bit at position m is 1 when we look at x minus y. The subtraction of x, y, okay, has an overall borrow bit that we call Tm. Remember, m is the width of the binary number that we're dealing with. So that leftover borrow bit is an indicator whether x, the first number, and y is less than y or not. Okay, let's go through a few examples, okay, because with this one, the best way to do it is to look at a few examples. So let's move on in the tablet. So we'll try a few examples. We'll try, okay, let's see, 0, 1, 1 minus 1, 0, 1. Okay. 1 minus 1 is a 0. There's an implicit 0 as the first borrow bit. Oh, this is it's lagging way, way, way behind. There we go. And 0 minus 0 is a 0. And then we got 1 minus 0 being a 1. Okay, it's taking a while. Okay, so we are talking about 1 minus 0 being a 1. And because the previous subtraction does not have any borrow, this is going to be a 0. So now we have 1 minus 0 being a 0 here. Okay. And then on the last column, we have 0 minus 1, which is the result of a 1. So we put a 1 here. But at the same time, 0 minus 1 has a borrow of 1. So we have to put a borrow here. And then 1 minus 0 is going to be a 1. And that concludes the whole subtraction. I really hate this part where it's so slow and it's having a hard time catching up with real time. There we go. Okay. Yep.
I have a question. On the middle one where you said 1 minus 0
Oh,
is 0.
yep. I made a mistake there. This one is supposed to be a 1. Thank you. So the middle difference bit should be a 1, not a 0. Okay, but yeah.
The row right above the second row, right after the subtraction, the first row after the subtraction, 0 minus 1, isn't that, no, 2 over, 0 minus 1,
0 minus 1 is a 1 with a borrow of 1.
I thought you have to write 0 and then with a borrow, 1.
No, this is the way I write it. Yeah, this is a subtraction. Oh, okay. Okay, yeah, 0 minus 1 is a 1 with a borrow. Okay, but it's the borrow that we're concerned about. So this borrow of 1 indicates that the value represented by 0, 1, 1 is less than the value represented by 1, 0, 1. What is 0, 1, 1 representing as an unsigned number? 3, okay, it's actually 3 whether it's signed or not, okay. What about 1, 0, 1 as a 3-bit number? Interpreted unsigned. What value is it representing? It's representing 1 plus 4, which is 5. 3 is less than 5 is true, and it's indicated by the borrow bit. Okay. If you flip the numbers in the subtraction, then it's going to be exactly the opposite. So I'm just going to do this really fast, and the computer is going to have some trouble, actually following through, but that's okay. Okay. So I'm just waiting for this whole thing to kind of go through, and then I'll explain it. I think this may be the better way to do it, is for me to just kind of zip through the whole calculation, wait for it to update, and then explain it after the fact. So 1 minus 1 is a 0. Okay, this 0 is assumed. 0 minus 0 is a 0. But since 1 minus 1 and 0 minus 0, neither of these contribute a borrow. So that's why the overall borrow is a 0 to the next column. 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. 1 minus 0 is a 1. 1 minus 1, which is the borrow from the previous column, is a 0. 1 minus 0 does not contribute a borrow. 1 minus 1 does not contribute a borrow either. So we have a 0 as the overall borrow of the entire subtraction. So the conclusion is the value represented by 101 is not less than the value represented by 011. Now we all know that it's greater than, but all I care is whether it is less than or not. And the answer is no, it is not less than. Okay? Because 101 unsigned is representing the value of 5. 011 is representing the value of 3. 5 is less than 3 is false. And the borrow bit indicates that. So are we okay so far? Okay, cool. So when you go back to the notes, it does go through a proof of sorts to convince you that we can look at that one single overall borrow bit. And it does indicate the correct result. Okay? But I'm not going to go through that proof, and you can read it on your own, okay, or we can look at it at some other time. So now the next slide talks about the sign interpretation. In other words, what if we are comparing numbers that are signed? Okay? What is a good way to indicate it? So the first question, or the first part, has to do with what value is that number representing? So I'm still using the same notation. M is representing the width of the bit pattern. And this time, I'm trying to find out what is the value represented by a binary number. And it is ugly this time because the value represented by a binary number in a signed fashion cannot just be a simple equation and just say, oh, we're just going to add up all the powers of 2 where there's a 1 in the digit. Okay? That doesn't work out anymore. So what we're going to do is to say, okay, we'll take a look at the last or the most significant bit. If the most significant bit is a 1, the number or the value represented is negative. So we use the ternary operator here, where this is the negative value represented. If x subscript m minus 1, the most significant bit, is a 0, then the signed number is representing something that is non-negative. So we use the third part of the ternary operator to represent that. Is that okay so far? So this bit here, the most significant bit of a signed number, is special. It is called the sign bit. Okay? Because if that bit is a 1, the quantity is negative. If that bit is a 0, the quantity is non-negative. Okay? So once again, m is the number of digits, and m minus 1 is the position of the most significant digit because we count from 0. Okay? So remember, we're counting from 0. Okay. So let's take a look at the first line here. So in the case of a non-negative value, it's easy. In the case of a non-negative value, we simply have to say, oh, we are just going to add up powers of 2 times the digit at position I. And if you just add up all of these terms, you'll be fine. Well, that's something that we saw in base conversion. Okay? Because all you're doing is look at each individual digit and multiply the value of the digit to the power of the base that the digit is corresponding to. That product is summed over all the digits, and that becomes the value represented by the binary number. Okay? So that's the easy one. This one is a little bit harder. So instead of staring at the equation, the number wheel can actually be helpful here. So let me go back to the number wheel on the tablet. This is one thing that's kind of nice about a tablet is I can just kind of go back to something that I was using earlier. Okay, so this is the number wheel, and this time we'll pay attention to the red numbers because those are the negative values represented in a signed representation. So now we ask the question, how can we look at, say, 110 and figure out that this is representing the quantity of -2? Okay, is there a way to look at this? We know the summation of all the digits add up to 6, but we know the actual value represented is -2. Let's look at the next one and see if we can find a pattern. 101, okay? Yep. Say that one more time. Is you have to subtract that from, right? Mm. Oh, you mean to figure out this -2? Yep, so that's one way to do it. But if I want to do it in a way to look at the individual bits without manipulating the bits first, the easier way to do it is to say, we'll figure out what, we'll add up all these digits and the powers of 2 that they are representing. So 101 will give us 5. And then what we do is we subtract 2 to the power 3 from it. 5 minus 8 is -3. 6 minus 8 is -2. 7 minus 8 is -1. 4 minus 8 is -4. Do you see how that pattern is working? Okay, so that is why, this is generalized in here as an equation. So let me go. I did something here to scroll off of that equation, but so I'm going to put it back here. There we go. So remember, the middle part is that portion. So we can look at the second line. It makes more sense here. So we are just adding up all the digits times the power of 2 that is corresponding to, just like with this one. But then we have to remember one thing. We're going to subtract 2 to the power of m from that stuff. Yes. Yep. But the most significant digit is at position m minus 1. M is actually 1 bit beyond the most significant digit. But we are subtracting 2 to the power of m as a quantity from this side to give us a negative value. How do we guarantee it is going to be a negative value? Okay, if I just look at this part here, okay, how can I guarantee that this is always going to be a negative value? No. Yes.
Because you said that the sums is using the most significant digit, and n is one more than that most significant digit.
It's a theorem that we proved earlier, right? Exactly. Okay, so I'm glad that some of you are able to connect this to the theorem that we have already talked about. And that's kind of how I want you guys to think about things, is look at something and then see how it relates to other things that we might have learned, either in the same lesson or in the previous lesson. So by making all of those connections, your brain is having multiple pathways to recall a particular concept. So yes, so that's basically what it is. So even if all the xi's are 1s, okay, this whole thing becomes, the sigma of I equals to 0 to m minus 1. Forget about xi because they're all 1s, 2 to the power of I. But we know that quantity has to be less than 2 to the power of m. That was proven earlier in the theorem. So we know that this is going to be a negative quantity. The only question is how negative. Okay. So from the second row to the third row, I didn't do anything to this side. Well, I actually did one thing. See how the index goes from 0 to m minus 1 in the row before, and now it's only going up to m minus 2. That's okay, because the only reason why we would be evaluating this one is when xm minus 1, or the most significant bit, is a 0. So if the most significant bit is a 0, it doesn't really matter whether we include that in the calculation or not. Okay. What about the middle one? Okay, this one is now expanded to this. What did I do? I just pulled the most significant term from the sigma on line 2 outside of it. I just move it out. So now it becomes this. And then the rest is the same. Okay, I just change the index by 1. Is that okay? Does everybody see what I did from the second row to the third row? in this particular expression, the last term has I equal to m minus 1. And over here, the last term has I equal to m minus 2. But how can I do that? Well, I pull that and put it into here. Okay, so it's algebra, but involving the sigma notation. And once again, the trick that I used was to pull terms at the very end of the sigma out of it. That was a hand. Yep.
Yeah, I understand that you do it from the left-hand side, but how about the right-hand side after the subtraction?
What about
Right-hand side.
this one?
Yeah, it's also.
This one I can do it because I know x subscript m minus 1 is a 0, so it doesn't contribute anything to the actual summation. Because remember, this is a ternary operator or ternary expression. The only reason I would be evaluating the third expression is when m minus 1, the most significant bit, is a 0. So I can do it only because of that. All right? Okay. So let's look at the third row versus the fourth row. Okay, what did I change? I changed this thing to just x subscript m minus 1 times 2 to the power of m minus 1. How can I do something like that? In other words, I'm looking at this first, okay, this part, and I ask, how can I change it to here? How can these two expressions be the same? Well, it can be the same because we know that if we're evaluating the second expression in a ternary expression, x subscript m minus 1 has to be a 1, right? So every time you see x subscript m minus 1, you might as well think of it as 1. Is that okay? This is 2 to the power of m. This is 2 to the power of m minus 1. How many 2 to the power of m minus 1 do we have in 2 to the power of m? 2 of them, okay? So if I know this is one of them, and there are 2 of these in here, and I take away 1, I got 1 left. Is that okay? All right. So, oh, wait. So that means I can pull this one back. Let's see here. So this is one expression. And then on this side, I go like, oh, I'm going to do the same subtraction here. But hold on a second here. We never had that term on the subtractive side. How can I put it on the subtractive side as the third term of the ternary expression? When we're talking about the third part of the ternary expression, what do we know about x subscript m minus 1? No, it's a 0, okay? So what do you get when you multiply 0 with whatever? You always get 0 back. So I can always add something like this because we know when we're evaluating the third part of a ternary expression, x subscript m minus 1 is already a 0. Of course, I can just subtract x subscript m minus 1 times something because that product is guaranteed a 0 anyway. Is that okay? But why would I do something like that? Because now the second term of the ternary expression and the third term of the ternary expression look exactly the same, which is great because they're the same. So that means I can use a single expression to tell me what is the value represented by a signed binary number or a binary number interpreted signed. Is that okay? More or less? Okay, so just to kind of make this concept gel by looking at more examples. Okay, let me see where we can find an empty spot. Okay, right here. So switching back to the tablet, I'm going to give you 2 examples as 3-bit numbers because that's still kind of fresh in our mind. In fact, I would use 110 as one and 010 as the other one. What values are these 2 things representing? I'm just using these 2 already on the board. Okay. So we use that equation. We look at the least significant bits, so everything except for the most significant bit. We look at the value represented by everything except for the most significant bit. These two, okay, that's 2, right? And then we say, okay, 2 minus 2 to the power of 2 is what? Is 2, is negative 2. This is 2, that's 4. 2 minus 4 is negative 2. So is 110 representing negative 2 in that number dial? It is. Okay, same here. So I'm using exactly the same approach here. I look at everything except for the most significant bit. Ignore that 0. It's just 10. 10 represents 2. Okay. Then I subtract the quantity represented by the most significant digit, which is 0 times 4 now, right? 0 times 4 is 0. So 2 minus 0 is 2. It works out. So that general equation to figure out what value is represented by a bit pattern, interpreted signed, does work out. I'm using this as an example to illustrate that. Are we okay with that? Okay. This is 2, and that is 2 as well. So we are looking at everything except for the most significant bit. Both of these binary numbers have 2 represented by the 10 as the part that is not excluding the most significant bit. Is that part okay? The 1 of the 110 is representing 4. The 0 is representing there are 0. There's 0. Is that okay? Because this digit is representing 2 to the power of 2, and I have one of those, and therefore this 1 tells me there's a 4. Right? On this side, this 0 tells me that we have 0 4s, which means the quantity that I need to be concerned about is 0. Is that okay? So now the value represented is 2 minus 4 in this case, and is 2 minus 0 in this case. So with 110, the value represented in the sign interpretation is 2 minus 4, which is negative 2. In the other one, it is 2 minus 0, which is 2. So I use exactly the same method, the same expression, to figure out the value represented by these two bits, bit representations. Is that okay? More or less? Okay, yep. There's no actual inversion of any kind. It's really just looking at the bits, looking at the values, and then do one subtraction based on the most significant bit. Yeah. Correct. So I'll give you one more example. Okay, so this time it's going to be a longer or wider bit number. So let's deal with 6 bits. Okay, so I have this 6-bit number like that. Okay, 101, 101 as a 6-bit number. Okay, so the first thing I need to do is to look at all the bits except for the most significant bit. I look at these 5 bits, the least significant 5 bits, and I ask what value do they represent? It's 1 plus 0 plus 4 plus 8. Okay, so that's 13. Very good. So this part alone is representing a quantity of 13. This one is telling us 1 of what? It's 1 of 2 to the power of 5 because we got 5 digits to its right-hand side. So what is 2 to the power of 5? 32. Okay, so we got 32. So the value represented in this case, so v of x, this is the binary number x. So v of x is 13 minus 32, which is negative 19, I think. catching up. There you go. So is that helpful? I mean, is this helping you understand that general equation? So we're doing the same thing, except we're doing it kind of mentally, because I'm just adding 1 times 1 plus 0 times 2 plus 1 times 4 plus 1 times 8 plus 0 times 16. Add it all up. That's our sigma term, which adds up to 13 in this case. Minus 2 to the power of 5 in this case, because m is 6, so m minus 1 is 5. So we subtract 1 times 32, which is 32, from the sigma value, and we get negative 19. So what this means is, using the signed interpretation, the 6-bit number 101101 represents the quantity of negative 19. Yep.
Can we assume that any number with a leading 0 and not a 1 is never going to be a negative quantity?
Say that one more time.
Can we assume that a binary number that has a leading 0 and that its last bit is not a 1, its quantity will be
Non-negative.
non-negative?
Correct. And that is also why the most significant bit is called the sign bit, because if the sign bit is 1, the quantity is guaranteed negative. If the sign bit is 0, the quantity is guaranteed non-negative. 0 is just non-negative. So are we good so far? Okay. So remember, the most significant bit is called the sign bit. So now we got 2 bits already introduced that might be helpful in comparison. One is called the sign bit, which is what we are talking about here. And then the other one is the overall borrow bit in a subtraction. Okay, that's the earlier part of today's lecture. Okay. So moving on from here. But the sign bit is not sufficient to tell us whether in a comparison a number is less than another number or not. Okay, it would seem that it should be able to do that, but it's not. Okay, so let's look at this derivation here. Let's assume, so x is less than y if and only if x minus y is less than y minus y. Does that make sense in algebra? You basically have a scale, okay, and you have it originally tipping like this, okay? And you remove the same amount of weight from both sides of the scale, it should still tip like that. Does it make sense? Okay. So, and then y minus y is just 0. Okay. There's nothing on one side of the scale, and then the other side is going to have x minus y as a quantity. So everything in this derivation makes sense. So the outcome is x is less than y if and only if the difference between x and y is less than 0. Is that making any sense? It should make sense, right? Wait, if x minus y, which is the difference, is less than 0, don't we have something that indicates, hey, this thing is negative in a signed representation? What was that called again? The sign bit. Oh, okay. So we can just look at the sign bit of a difference after a subtraction, and then we should be able to tell whether the minuend is less than the subtrahend. I think the x is called the minuend and y is called the subtrahend. Is that right? Okay. So it should work, right? Except sometimes the sign bit would lie. So the sign bit is like me, okay? Its conscientiousness is not exactly very high. It's not at 100%. So we have a problem. Okay, so why would that even happen? I mean, it doesn't seem to make sense. I think with this part I can use Notepad maybe faster because I don't like the lag. So I have to fix that problem at some point, but right now I'll just use mousepad. Okay, so I'll give you a few examples. I'll give you one example where the sign bit is going to lie, okay, and therefore we have a problem. Okay, so let me see. Okay, this will work. So 0, 1, 0 minus 1, 0, 1. Yeah, that should work. Let's see. Okay, let's figure out what this one is going to be. I'm not 100% sure whether this will work in the case that I want anyway, but it's still going to be useful. So we'll go ahead and finish this subtraction here. All right, 0 minus 1 is a 1 with a borrow, like that. And then 1 minus 0 is just a 1. And then over here we have 1 minus 0 being a 1, 1 minus 1 being a 0, like that. And then over here we got 0 minus 1 being a 1 with a borrow. So we put a borrow here. And then we have no borrow from the previous column, so this borrow is going to be a 0. And so 1 minus 0 is going to be a 1. Okay, so let me just double check the math and make sure it's right. 0 minus 1 has a borrow, and the result of 1. 1 minus 0 is a 1. 1 minus 0 is a 1. 1 minus 1 is a 0. 0 minus 1 is 1 with a borrow. 1 minus 0 is a 1. So I think that is correct. Okay. So remember what I said? The sign should be able to confirm whether the minuend, the first number, x, is less than the subtrahend, which is the second number, y. Okay? So let's see whether that makes sense or not. So what we'll do is we look at what 0, 1, 0 is really representing as a quantity. It's 2. Okay? And then we'll look at 1, 0, 1 and see what it is representing in a signed way. Okay? So 1, 0, 1 is representing what signed? Is a negative value. So let's apply what we just learned, right? We add up all the, we look at everything except for the most significant bit and see what it's representing. In this case, 0, 1 is representing 1. And that one, the most significant bit is for which quantity, which power of 2? 2 to the power of 2, which is 4. 1 minus 4 is negative 3. Okay, so 1, 0, 1 represents negative 3. Okay, so we got negative 3 here. Okay. Is 2 less than negative 3? No. But what is the sign bit of the difference? This difference is this row. What is the sign bit? The sign bit is a 1 because it's the most significant bit of that number. So the sign bit is a 1 and yet it's lying. The sign bit is saying, yeah, 1, 0, 1, 0 should be less than 1, 0, 1, but it's not the case. Because 0, 1, 0 is representing 2, 1, 0, 1 is representing negative 3. It doesn't seem to work. Why is it not working? If you look at 1, 0, 1, tell me again what is 1, 0, 1 representing in a signed interpretation? Negative 3, right? So why is 2 minus negative 3, negative 3? What should it be instead? It should be 5, right? 2 minus negative 3 should be 5, and yet it gives me negative 3. Why? Where's that 5 on the number wheel? In signed interpretation, there's no 5 on the number wheel. In other words, we came up with a quantity that could not be represented using only 3 bits. That's the problem. So that's why this condition is also called an overflow condition. Yep.
Is that why there's that carry bit at the end?
You mean the borrow bit?
Yeah, the borrow bit.
The borrow bit is useless for signed comparison. It is only useful for unsigned comparison. But as soon as you say, oh, all of these numbers are representing signed numbers, then you don't look at the borrow bit at all. That is completely useless for signed comparison. Okay? But the signed bit alone is useless as well. Right? So what are we going to do? Well, so what we need to do now is to say, okay, so how can we tell that there's an overflow situation? Okay, you can look at the overflow situation as the sign bit cannot be trusted anymore. Okay? So I'll give you the 2 scenarios, or the 4 scenarios, and I'm going to spell out the subtraction like this. So I'll still use x, in this case, this is x2, x1, x0, minus y2, y1, y0. So x and y are the numbers. X is the minuend, y is the subtrahend. And then we go through a whole bunch of subtraction stuff and whatnot. We end up with d2, d1, and d0. Okay, so the d's are the bits of the difference. The x is the minuend, and then the y is the subtrahend. Okay, that's the subtraction that we're dealing with. Tell me how you can tell that we have an overflow situation where the sign of the result doesn't make sense. Okay, let's look at the 4 combinations, because the x and the y we can control, those are the inputs. The d is kind of the result of the calculation, so we cannot really quite control that, but it is one of the factors. So when I look at this table, okay, so we'll look at x2, y2, and d2, and then we will say, does d2 make sense? Okay, and this table is going to be a little bit long because it has got 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, whoops, 0, 1, 1, 1, 0, 1, 1, 1. Okay, yep, that looks right to me. All right, so tell me, does that make sense? Tell me again, what does it mean when x2 is a 0? What kind of value is x representing? I just need to know whether it's negative or not. It's not negative. It's not negative. Okay. So I'm subtracting a non-negative value, which is y, from a non-negative value x, and the result is non-negative. Can that happen? 1 minus 1 is 0. And they're all non-negative, right? So it can happen. Okay. So we'll say it makes sense. Okay, so we'll say yes. Okay, what about this one? I subtract a non-negative value from a non-negative value, and the result is negative because the result has the sign bit being a 1, which means it's representing something that's negative. Let's see. 1 minus 2 is negative 1. Okay, can happen, sure. Yes. Okay, what about this one? I'm subtracting a negative value from a non-negative value, and I end up with a non-negative value. Does that make sense? 1 minus negative 1 is 2. Oh, okay, that makes sense. Okay. And what about this one? I'm subtracting a negative quantity from a non-negative quantity, but the result is negative. That doesn't make sense. Okay, so we'll say no, and I'll ignore online email etiquette and use all uppercase here, because we do have to emphasize that this is a special case. What about this one then? I'm subtracting a non-negative quantity from a negative quantity and ending up with a non-negative quantity. Does that make sense? Nope, should never happen, right? So we'll say no here. And what about this guy here? We are subtracting a non-negative quantity from a negative quantity and end up with a negative quantity. Does that make sense? Yeah, okay. Negative 1 minus 1 is negative 2. Yeah, sure, makes sense. Okay, so we say yes. What about this one? We are subtracting a negative quantity from another negative quantity, and it ends up to be negative as well. Does that make sense? Can it happen? What happens when you subtract negative 1 from negative 2? What do you get? Let me say that one more time. You're subtracting negative 1 from negative 2. You should get negative 1, right? So it can happen, okay? So it doesn't make sense. And the last one is you are, oops, okay. What I just said is this one, no, this is the other one. So this one we still have to figure out. we are subtracting a negative quantity from another negative quantity, and it ends up to be positive. 1 minus negative 2 is 1. Okay, well, that can happen. So we only have 2 rows here that are kind of special, where it cannot happen. Or when you see something like that, the sign is going to be wrong, okay? Because we ran out of digits to represent the result. So we are talking about the 0, 1, 1 and the 1, 0, 0 row. Okay, great. So what? You have a lie detector for the sign bit. We can tell whether the sign bit is lying or not. Yep. Hmm? Because because your processor has a fixed width for processing, integers. So that's why, if you have an 8-bit processor, you're stuck with only 8 bits. If you have a 16-bit processor, you're stuck with only 16 bits. So we cannot make it any wider, but we can still be we should still be able to tell whether the intended sign should be a 1 or a 0. Okay. So we'll take a look at these 2 scenarios. 0, 1, 1 first. So we look at 0, 1, 1, and what is it saying? The no. Okay, let me highlight it first, so this way it's easier to visually see what scenario we are talking about here. So we're looking at this scenario. We know that this is overflowing. The sign of the result does not make sense. So what should it be in the first place? Okay, so think about it like this. So the sign bit is like a person, who can only say yes or no, okay? And we have a lie detector that can say whether the sign bit is lying or not. And once again, whether the sign bit is lying or not is also a yes or no, right? So in this particular scenario, the sign bit says yes. The lie detector also says yes. So what should be the sign? What do you think is the sign of what? I'm restructuring the grammar here. The actual sign of the result, what should it have been? Huh? It should be a 0. The sign should have been a 0. How do we know it should have been a 0? Because the sign bit says, yep. The lie detector said, nope, he's lying. Right? Okay, wait. The sign bit is saying yes, but we also know the sign bit is lying, and it can only say yes or no, right? So the correct answer should have been a no. Is that making any sense? Okay. What about the next one? The next one is this one here. Okay, it's the same kind of deal, okay? The sign bit is saying no. The lie detector said the sign bit is lying. So what do you think the sign bit should have said? Yes. All right. So that means in all of these cases, we should be able to tell whether x is less than y. Okay, so now we go for the last column here, which is only going to say x is less than y. Is x less than y? So anytime the sign bit is not lying, which means does D2 make sense? If it is a yes, we can rely on D2 entirely to say whether x is less than y. So it's a no here, it's a yes here, it's a no here. But when it does lie, okay, when we have something like this where D2 does not make sense, that means the sign bit is lying. D2 is lying. But D2 says 1, and is lying means that D2 should have been a 0, which means it is the intended answer should have been a no. Okay, x is less than y should have been a no, even though the sign bit says yes, because we know it is lying. Is that okay? Okay, what about this one? The sign bit says no, but we know it's lying. So they should have said yes, right? And what about this one? This one says, the sign bit is not lying. So whatever the sign bit says is fine. So we say yes here, and then we say no here, and then we say yes here. So now we can say we can now deterministically say whether x is less than y, no matter which case it is. Is that okay? All right? So everywhere it is saying no, it means x is not less than y. Everything where it says yes, it means x is in fact less than y. So we can tell, okay, from only looking at the most significant bits of the minuend, which is x, the subtrahend, which is y, and the difference, which is d, we can now deterministically say whether x is less than y, which is great, okay? All right, so just one more thing before the lab, because the lab does require this particular part. Okay, so just two more things. So we defined overflow to be when so overflow is true when the sign bit is lying, okay? In other words, I need some kind of expression to be true when one of these two rows is happening. So how should I express that? The first one is not x2, y2, d2, and then we have to OR that with the next one, which is x2, not y2, not d2. So this expression defines overflow. This is not a zero. It is an uppercase O, which stands for overflow. You can look at overflow as the lie detector of the sign bit. Okay? So if the overflow bit is a 1, it means the sign bit is lying. Yeah? Say that one more time. Okay, so the overflow flag is the lie detector of the sign bit. When overflow is a 1, the sign bit is lying. Okay? Does that make sense to you? Because this one is 0, 1, 1. 0, 1, 1 means that if I want this combination to give me a 1, I have to negate the x2 first, and then end it with y2, end it with d2. That conjunction is going to give me a 1 for the 0, 1, 1 row. Is that okay? But what about the next row? When x2 is a 1, y2 is a 0, d2 is also a 0. Then we just go for the kind of the opposite. And then just one more thing. I know Mr. Fox is waiting outside. The next one is the L bit. The L bit is the overflow exclusive OR with the sign bit. In other words, the L bit is the conclusive answer of whether x is less than y or not. Why is it the exclusive OR? If exactly 1 is true, then the whole expression is true. So let's think about the 4 possible ways. Okay? So let's think of the ways when overflow is 0. The overflow is 0. Sign flag says 1. The result should be 1. Why? Because the sign flag is not lying and is saying yes, so the overall answer should be yes. What about overflow being a 0, but the sign flag is a 0? Well, the sign flag is not lying, so if the sign flag is not less than, it should not be less than. Okay? What if the overflow is a 1 and the sign flag is a 0? Well, the sign flag is lying, it's saying it is not less than, so it really should have been less than. Okay? What if the overflow is a 1 and the sign flag is also a 1? The sign flag is lying. It is saying x is less than y. What should have been the answer? Not less than. Yep. So that's why the L flag, which truly reflects whether x is less than y, is the exclusive OR between the overflow and the sign flag. Now you guys get all the information you need for the lab. Just need that last little push. Okay, so we'll go over to the lab, and this one takes the highest score, but you can